Right, and I'm here to introduce Isabelle because that's a system I've been working with for the last 13 years. So yeah, it's an interactive theorem prover, and the people who spoke before me already introduced a lot of the basics about these things. So I'm very grateful because now I don't have to repeat these things. So it is quite old. Like all the ones except for lean, I think, are relatively old. And the basic idea, as you've seen before in the other systems, is that you have this relatively small kernel. How small that actually is a matter of debate. So some people say we have the smallest microkernel in the world. So the basic idea is you break all the reasoning you do down into very, very basic logical steps, and the kernel only understands these basic logical steps. So if you trust that these are implemented correctly in the kernel, then you can trust that everything works. And so Isabelle is a generic proof of system, so in principle it can do all kinds of different logics, and you can set up your own logic with your own axioms, and in practice people almost entirely use higher order logic, so that's Isabelle Hall, is with higher order logic. There are some people using Isabelle ZF, so Zemmel-Frankel logic, but I think that's pretty much all of them, so all the other ones, I think people used them like in the early 90s, but they never really got anywhere. And yeah, the logic is relatively simple, so it's similar to stuff we saw in Hall 4 or Light. So it doesn't have dependent types compared to Coq and Lean. And some people say you need dependent types, other people say you never need dependent types. So the thing is, in my opinion, sometimes dependent types allow you to write things in a nicer, more natural way, but they also come with certain downsides. So it's not entirely clear. Yeah, I think you can do without them if you want to, and
it's a research problem. No? I think that's all.
In some sense, it is. Yeah. So Larry Paulson always said, it's a good thing we have all these different systems with different logics, and we just do the work in whichever one we feel most comfortable in, and then we let history decide.
So when type theory friends ask me about why dependent types are necessary, I say, well, in math we like to make statements like for all natural numbers n equals n. So how do you do math without that?
So for all natural numbers
n equals n.
N equals n is not a type.
N equals n is not a type. That's true.
Not in Isabelle, yes. So we have no problem formulating using quantifiers in Isabelle at all. So I'm not a logician or anything. So that's the other thing. So one cultural difference between Isabelle and Coq, in my opinion, is Isabelle people do not care about axioms. They never talk about axioms. They just use the system and they use what's there and it works. And there's just, there's no discussion about, do we use the law of excluded middle or the axiom of choice. Like most people aren't even aware that this is a thing. Like most mathematicians, I would say. That's for you to decide. Right, and I would say the focus is good automation, high performance, and parallelism. So it was one of the first systems that actually had parallelism, and I think many still don't. So proofs can be checked fully in parallel, and that works quite well. So we have a very, very large library. I just checked before, so we have, I think, about 800,000 lines in the core distribution, and about 5 million lines in the archive of formal proofs. That does include blank lines and comments, because I couldn't figure out a quick way to not count these, but still, it's pretty big. So yeah, we have a large library of mathematics. So we also have stuff that's not mathematics, but that's not what you care about, so I already talked about the mathematics today. Especially one field where I'd say Isabelle is quite strong is analysis. So algebra, not quite as much, but yeah, so analysis is pretty good. And there is a thing called the Archive of Formal Proofs, of which I'm also one of the editors. And so basically this is just a big collection of community-contributed proofs, proof developments really. So basically it consists of these entries or articles, and they're all about like one specific topic, and basically anyone can submit one there. And basically if it's not absolute nonsense, it just gets accepted. So it's a bit like a scientific journal, but it's more in the sense of let me finish. It's more like a data repository where basically people submit scientific data, and that data just then gets stored there, and it's also maintained in the sense that if Isabelle keeps developing, If anything breaks stuff in the archive-performing proofs, then the stuff in the archive-performing proofs, they have to also fix everything in the archive-performing proofs. So this is really stable and it continues to work. So it's not like, it doesn't have, there's no rigorous kind of reviewing in the sense of a scientific journal. Of course, we look at the stuff, and if we say, well, okay, what you're writing here is not at all what this theorem is supposed to mean informally, then we're going to complain. Or if there's like stylistic problems, but the focus is really just on, well, the proofs should work, and then they get accepted. Yeah, so the history of Isabelle, it was started by Larry Paulson in Cambridge, and it came out of a whole family of provers, I would say, LCF-style provers. The core these days is mainly developed, or I should say maintained by Makarios Wenzel. I think maintained is kind of a better word because, well, he makes performance improvements and that sort of thing, but the core is relatively stable in the sense that there's like nothing big going on there for most of the time. And so the rest of the stuff, there are contributions from all kinds of people, mainly PhD students in Munich. They are quite active. So these are all both proofs, so we extend the library, the basic library. We also maybe improve some stuff like some automation, some tooling, but this is not really at the core of Isabelle. So the core of Isabelle, I think, doesn't really change very much anymore, and we're a little bit limited in how much we can change it as well, because if we break 5 million lines of code in the AFP, that there's very few changes that are worth that sort of thing. So yeah, one big change in 2005 were structured proofs. So I'm going to show this in a second. So Isabelle has readable proofs, is what people like to say. How readable they are is up for discussion, I guess. So a lot of people say that it still kind of looks ugly, but I mean, it's formal maths, right? So you have to be very precise about what you say. You cannot omit any details. So I always say that when you write paper proofs, you outsource a lot of the work to the reader, both in interpreting what's there and in checking side conditions, etc. And when you do that in a theorem prover, you have to be very explicit, and then things just become a lot more verbose and, well, possibly ugly. And that's just very difficult to avoid. But I claim that one point of evidence that we have relatively readable proofs is that the lean people keep stealing them. So they keep porting our Isabelle proofs over to Lean. The reverse direction I've tried is much more difficult. So I claim that they are at least somewhat readable. And yeah, then the archive formal proofs has been around for 20 years. And yeah, now I'm just going to show you some examples to get an idea of what Isabelle looks like. So, well, some mathematics we have in Isabelle, just an overview. So for instance, I proved this a few years ago. It's a relatively small thing, that the volume of an n-dimensional ball is this thing. So we have, you can see also the gamma function. And of course, we also have more explicit expressions for that, depending on whether the n is even or odd. We have the prime number theorem, that's very recent, so we've had the prime number theorem for a long time, but we now also have a version with a very explicit error bound due to a Chinese person whose name I forgot, unfortunately. Yeah, this is quite recent. Eberl's theorem, which is that zeta of 3 is irrational, so yeah, we also have the Riemann zeta function. So I would say we really have like non-trivial maths, right? The central limit theorem, the law of large numbers, so some probability theory, the existence of the algebraic field, algebraic closure of a field, so that's some non-trivial bit of algebra. Linnemann-Weierstrass, that's one that I formalized a few years ago. So basically that, is something like e to the something plus e to the something will typically not be 0, and in most cases that sort of thing. And then, yeah, we formalized 1.5 textbooks on analytic number theory. So that's stuff like the prime number theorem. Recently, we did like basis of modular forms. So really advanced analytic number theory, I would say.
How many textbooks of analytic number theory exist?
I have no idea. Yeah. I mean, I kind of got into this by accident, and now I just continue formalizing stuff. But yeah, so this. I mean, these were like more like introductory textbooks for students. So this is not like a monograph or something, but still, I think if we want to download that, we have a pretty good basis on which to continue with more stuff of modular forms. Right, then we have lots and lots more of stuff in particular, we have a huge amount of probability theory, Markov decision processes, that sort of thing. We have a lot of complex analysis, which you also need for the number theory. And there's extensive work on differential equations as well. So there's a fully verified numerical solver for ODEs, which was used in a formal proof, something about the existence of the Lorentz attractor. So it's really a huge amount of material. Right, so some concrete examples, what does an Isabelle proof look like? So that's a very simple example that I encountered, I think, a few years ago. You have some, well, you can think of it as a complex number with a norm less than or equal 1/2, and you want to show that an e to the z is the norm is less or equal 1 + 2 times the norm of z. I think it works in more general cases. I think it works for any kind of Banach space or something like that. Right, so in Isabelle it kind of looks like this. I wrote these little quotation marks here. I think most people use just regular quotation marks in Isabelle. That also works, but that's kind of the modern style that nobody uses. Never mind that. And then the proof basically looks like this. It's a very simple proof, of course. Right, you should say the norm of an exponential is less than or equal to the exponential of the norm. That's already in the library. And then you approximate this by some truncation of the Taylor series of the exponential function on the real numbers now, because right, this is real number, the norm. And then because z is less than, the norm of z is less or equal to 1/2, then you can also approximate this power like this. And then you're already done. And then all you have to do to make this an actual Isabelle proof is you have to justify every single step in that proof. So you have to fill in these lines. And these are essentially tactics, but we don't like to write these huge chains of tactics that manipulate some implicit proof state, but we rather make like steps from one line to the next, where each step is justified by a very small tactic. So that can be either here, it's just a single application of this norm X rule, which says, well, exactly that. Or it could be we feed in some facts that we already have, and then we call auto, which is just some general automation tool that is used most of the time. Or we can say, well, I want to use some explicit rule, which says that, well, the power on some ordered, whatever it is, ordered ring is decreasing under certain conditions, and then the side conditions that arise from these, so some stuff like the norm of z has to be less or equal to 1 or something like that, this we just hit again with the automation after we feed in the assumption up here. And then the final result, we just do one step of simplification. We could also do auto here, it doesn't really matter. So that's the basic kind of structure. And of course, there's much more that you can do. You can also do case distinctions, you can do induction, you can say, well, okay, I know that there exists some x with these properties, then you can obtain an x with these properties. But that's kind of the basic idea. And of course, you can nest proofs as well. And so most proofs will be a lot ugly and a lot bigger than this, but that's the basic idea. Right, so another result that we have is, for instance, this formula for the Riemann-Zeta function. So, as you can see, it looks like not super unlike, it looks somewhat unlike mathematics, classical mathematics, but I would say that it's still somewhat readable. Right, so you say, well, this power is just a power operation on complex numbers or real numbers. The reason why we don't just write it as the normal power is that, well, you have a power that takes something you can multiply and has a neutral element, and a second argument is a natural number. That's one power operation. Or you can have a power operation where you have a field and an integer as the exponent, or you can have something more general where you have like complex numbers or real numbers, and all of these are kind of like in mathematics, you write all of them as a power symbol, but if you want to do things formally, you have to be a bit more precise and actually distinguish these because they all have very different properties. So that's why we write this as its power. The rest I think is fairly standard, and then instead of writing this integral as an equality, we actually write it as a relation has integral. The reason for that being that, well, just because you write down an integral like that doesn't mean it actually exists. So we kind of combine the fact that the integral exists and it has this value into one single relation, and that makes things a bit easier. So I guess not too surprising.
Are the curly brackets over there the limits of the integral?
Yes, yeah. So this is basically the set that you're integrating over. And in this case, that's the set from 0 to infinity, and the 0 is not included, not that it makes a difference. You can actually prove that it doesn't matter whether you include the 0 or not. But yeah, so these are basically the integral bounds in a sense.
But the two dots are infinity, or is something omitted in the...
No, that's basically what you write is you write curly bracket a dot dot b. That's the integral. That's the interval from a to b with both limit points included. And then if you leave out one of the limit points, then it just goes to infinity.
But I guess that is what I'm wondering if that syntax is like user defined, let's say.
It is. So everything in Isabelle in some sense is user defined. So you can at any point you can integrate new syntax into the system. Also, this has integral. That this infix operator has integral. It's also user defined. You can even at any point basically you can modify the type checking and the parsing. You can like put hooks in there and do arbitrary stuff. Very complicated.
The Lima assumes shows that's all built in.
So yeah, well, it depends on what you mean by built-in. So you can also make new commands like lemma.
Okay.
So in some sense, lemma and assumes and shows is also user-defined, and people have done things like that. Yeah.
So for x is 0, you divide by 0, right? So you said
Yes.
if you do the inclusive thing, so what is the value of that lambda term if x is 0?
So in Isabelle, like in Lean and Kocken, to my knowledge, anything divided by 0 is 0 by definition. And mathematicians always, scoff at that. The thing is, it doesn't matter. It's not a problem, right? It's
PVS, then you don't need to do that.
I know this is a long-standing controversy, but I assure you, it's not a problem. In this particular case, anyway, it doesn't matter because, well, you can prove that any two integrals that differ by like a finite number of points are equal anyway. So whether you include the 0 or not, it doesn't matter, no matter what value you put there. And so basically, experience has shown that, of course, you can in dependently typed systems you could do something where like, well, my division operator takes as a second parameter a non-zero input. You can do that, and then you have to prove every time that you use division that the thing isn't 0. But to my knowledge, nobody does that. Like in no system, not even in Lean and Koch, who could easily do that. They do that because it's just causes lots of headaches.
What about PVS?
I have no idea about PBS. I'm sorry. Right. So yeah, prime number theorem. I mentioned that one as well. So this is the easy version without the error term. So this basically just says, well, the function taking some real number x and returning the cardinality of the primes less than x, less than or equal to x, is asymptotically equivalent. So again, that's user-defined notation to x divided by log x. Not too surprising, I guess. Dirichlet's theorem, which says that if you have two coprime numbers, h and n, then there are infinitely many primes congruent to h modulo n. Looks like this. So again, there's some user-defined notation for this congruence relation modulo some number.
What kind of infinity notion do you use?
I mean, in classical mathematics, there really is only one, I think.
Sure.
Yeah, so I don't actually remember what it is defined as, but whatever infinity you're thinking of is probably equivalent to it in whole. So,
finite.
5 minutes. Okay. Oh yeah, this is going to be tough. Okay, Stirling's formula. I'm going to skip over that a little bit. Yeah, we have Stirling's formula as well. We also have it in the complex plane with a gamma function, etc. I'm not going to go into detail here. So I'm just going to leave this up and I'm going to show you some. I'm just going to continue to a short little demo that I prepared 5 minutes ago.
Sorry, another question. Do the quotes, what do the quotes do? They introduce like...
So the quotes separate outer syntax from inner syntax. So outer syntax is relatively rigid, you cannot really do much there. Inner syntax is completely user-defined. And I'm not sure whether this separation between outer and inner syntax is really necessary, but it's just historic that you distinguish the syntax of types and terms from everything that happens around it in the system. And you could probably, in theory, get rid of it, but yeah, it's just one of these Isabelle quirks. Right, so what I did here is I just defined the notion of a prime number. Of course, prime numbers are in the library, but it's kind of silly if I present you the proof of infinitude of primes and it's already in the library. So I just defined this notion here as well. A number is prime if it is greater than 1, And for all numbers between 1 and n, the k does not divide n. And then you can prove just by simplification that 0 isn't prime, 1 isn't prime. I'm writing successor of 0 here because just by convention, a 1 of the natural numbers gets rewritten to successor of 0, so it's better to have this as a rewriting rule. 2 is prime. Then you can prove by induction that every number greater than 1 has a prime divisor. You just do induction with the rule less induct, which allows you to assume in the induction hypothesis that you have a number smaller than that number. And so I'm not going to show you that proof in much detail, so I just wanted to get a feeling of what it looks like to write an actual Isabelle proof. So now I want to show that whenever I have some finite set of numbers, then there is a prime number that isn't in that set of numbers. And the way I do this is I do a case distinction first, whether this set contains only 0 or something more than 0. So when it contains only 0, then it's pretty easy, because then we can just use the fact that 2 is a prime number, and that should already do it, yes. So you just feed that factor auto and you're done. And if there is something that isn't 0, then what you do is, well, you say, okay, I define n as the product of all the numbers in A minus 0 plus 1. And then what was it? Then we know that n is greater than 1. Let's see. So now I don't really know how to do this, so let's just ask Sledgehammer, because I'm too lazy to do this myself. And the Sledgehammer, what that does is it translates your problem into some language that certain automated theorem provers can understand and feeds it to them. And then, okay, in this case it's quite easy.
Where does ndef come from?
From this definition here. So from this define command. This define command, well, it kind of fixes a local variable n and assumes that this is equal to this term on the right-hand side and calls this fact ndef. And then in the end, when I finish my proof, then this gets eliminated again, so that this assumption is kind of, we get rid of that one. Okay, then we know that there is a prime divisor of n, like this one. Let's use auto here. And right, then what we want is...
What's the difference in blast and auto?
Beg your pardon?
What's the difference in blast and auto?
It's just different automations, and they're good at different things. So I just instinctively, when I see a goal where I think, okay, Blast is good at this, I use Blast, but you get a feeling for these. So there's a lot of different automation things, and some of them are better at some things than others. Well, no, what do we want? We want P not in A. Let's see if we can do this. Let's just feed in everything we have. Let's unfold the ndef as well. Oh yeah. So when you do more advanced mathematics, Sledgehammer is not quite as good as it is here, but still it's used a lot, and it's very helpful. And we're done. And now we can also show that set of prime is infinite. Yeah, just like that. And I can assure you, if you try this yourself, it's going to take you much longer. And also the first time I tried this before, it took me much longer. And then one of the reasons why it was so short now was that I realized that Sledgehammer can actually do much more than I thought it would be able to. So yeah, but this is like not unlike how I usually do stuff in Isabelle. And so the automation really is very, very good, and it can eliminate a lot of tedious reasoning. And in some cases, the end result is actually fairly readable. So I would say here it is actually quite readable. So yeah, if you want to do some maths in Isabelle, then come and see me, but you better bring your own ideas along, because I don't have very much prepared, I'm afraid, because I only heard that I have to do this last Thursday, I think. So,
You will figure it out.
but yeah, we'll figure something out.
Thanks a lot.